Well, fantastic, okay. So, good morning everyone, and today I'd like to talk about ore deposits, and this is an introduction to ore deposits, being one of the... Good morning, we already started. So, this is an introduction to ore deposits, and it's really a starting point for you guys. So, we're going to start with some general points on ore deposits, and then we're going to move towards individual deposit types. So, what is this all about? It's about natural resources, one of the critical issues of our days. And here we're talking about land or raw materials that occur in a natural form within our environment. And we have so far not really taken control of them. And to make use of these, we need to consider a whole range of factors. Geological factors, economic factors, environmental factors, increasingly important. Marketing becomes an issue as well. As you probably all know, the iron price is rising again. There's a lot of excitement about this in the ore petrology and ore community, and hopefully it's continued to rise for the next little while. There's often governmental issues, societal factors. We talked about blood diamonds the other day, for example. So some of these resources, they are ethically not entirely clean. Others are, but that requires a lot of effort. So we will focus today mainly on mineral resources, and in particular on metallic ones. So this is the concept of today, and all of you guys, you will have the opportunity to listen to more detailed lectures on this. There's ore deposit courses later on in the master's program, so you can hook up with those courses should you wish that. But for those who are not, you can use this as a little introduction to give you a flavor of what this is all about. What is a mineral deposit? It's a locally enriched concentration of minerals, and for that we usually have a geological reason. These local enrichments don't occur randomly. There are geological processes behind that. What is an ore? It's a resource of metals usually. When we use the word ore, it implies there's a metal resource involved, and we want to economically extract this, so the idea is that somebody makes money with it. Mineral reserves is a known deposit of earth materials. Doesn't have to be a metal, it's just about minerals, could be aggregate type things as well, which are useful in some form or another, and which we can in theory recover with our technology. An ore deposit is the same as a reserve, but here we are really a step further. We have a concentration and we have a good idea of what this is, and we may want to go at extracting this. The distribution of mineral resources, they are highly localized. As I said, they are not randomly distributed. There is some processes that have made them concentrate in a certain way and in a certain place, and it's our job to understand how this comes about. So the concentration of valuable mineral deposits is often due to special, sometimes even unique circumstances. Places like Kiruna, for example, it seems unique in the world, is one of the largest iron ore deposits in Europe, certainly, and there is some other examples around the globe, but Kiruna is certainly unparalleled within Europe, so there must be something unique to it, at least on a European level. Sweden has a long mining tradition. It's going back well over 1,000 years, and it's been less well organized 1,000 years ago. It was mainly private enterprises, but in the late Middle Ages and also in newer times, it became more and more organized. The king took control over this, over many mining operations in the 18th century, and some of them have been governmentally organized, and LKAB is still governmentally run to this day. That's the company that mines Kiruna. Sweden is the top 3 producer of copper, lead, and several other metals, gold, etc., and it's the biggest for iron. Iron is, despite all the talk about rare earth elements, iron is still the most important metal for modern industry. Think about building a bridge, you need iron for that. Think about building a car, you need iron for that. So iron is fundamentally important, although there's always hype about rare earth elements and critical metals that we need for green technologies, for IT, applications and things like that. But without iron, our economy wouldn't work the way it does. So here's a few impressions going back into Swedish mining history. Here's an old drawing about a shaft, and here's a bucket, and you can either bring rocks down or people down or up, depending on. And this is from Igneous here in Bergslagen. This was a mine that was operational until the 1980s, and here you see the miners proudly posing in front of one of the mine buildings. Here, it's a little train that's depicted, that's in Igneous. These images are from the 1950s, and you see it's got more modern with time. But this particular mine was shut down in the 1980s. People say mainly for political reasons. There's still a lot of ore left. And Kiruna has been overshadowing many of these operations further south, because Kiruna is just so large and so massive that it becomes tricky to be economical when you're competing with such a large operation. Just to give you a feel, Kiruna has something like 40 kilometers of roads underground. They're driving with trucks there that you wouldn't see on our roads here. They're so big. So there's almost, if you will, a whole traffic network and a little city down there. There's a restaurant down there and things like that in the mine. It's going down to what's known as the deepest place in Sweden. It's a huge operation. So here's a few more impressions of how mechanized mining works today, and from Kiruna to any other mine, there is a lot of monitoring going on these days. There's a lot of exploration within the mine going on, trying to see where the best next shaft is produced, how to best get the ore out, and of course safety and environmental concerns becoming more important in that respect as well. So let's talk a little bit about concentration factors. Here we have different metals: aluminium, copper, gold, iron, lead, mercury, silicon, and titanium. We don't need to look at them all, but just to give you a feel, here we have aluminium, and the average in the Earth crust, it's a percentage, is about 8%. And if you really want to make money of it, if you want to make it economically viable, you need to have enrichment on the order of 35%. So for copper, we have 0.0063, and you need to have concentrations of about 0.8, better even 1% or so. And here the concentration factor relative to average continental crust is over 100 in many places. Otherwise, it's not economically viable. For gold, well, it's very little in average rocks, and you need to have quite a bit of a concentration for it. The concentration factor is about 2,500 in economically viable deposits relative to the average continental crust, and you get a feel for the enrichment that is needed. For iron, we need concentrations of, well, several tenths of percent, and here the enrichment factor is between 4 and 14. So for lead, we also have a very high factor here. So you get an idea that it's strong concentrations that are important in order to make mining viable. Here is a plot, the abundance of atoms, and here we have atomic numbers, and you have this zigzag phenomenon. We talked about it in geochemistry. That's going back to the Otto Harkins issue, and here we can distinguish different metals that are relatively important for us. So major industrial metals here are in red. So here we have copper, zinc, nickel, there's tin, molybdenum, etc. And in purple we have precious metals. So here is silver, and here's palladium and platinum, and here's gold and iridium. And then we have rare earth elements. They're also very important. And they're given in blue. They mainly fall into this part of the diagram. Here we have La Toulouse, we talked about it in geochemistry as well, and all the lanthanides, for example, fall into that area as well. Here is a plot of world production, in this case for manganese and for aluminium. And here's manganese, aluminium, and here's a timeline, 1950 to 1980, so 1990 is not fully up to date here, but I think the trends are very, very striking. We have an increase in demand with time, and this is not really stopping. It seems to plateau here a little, but ultimately it's a rising curve, and we see similar things here for lead, copper and zinc. And while plateaus may occur, often there is a continuous rise, and certain fashions on the market may determine whether a certain element or a certain metal is needed in super high demand, or it's a little less sincere or a little bit less intense for demand at some point. But overall, many of these metals are in rising demand, and so is iron. There is no way around. We need more metals, in fact, in order to keep our lifestyle and our social system functioning. And if we want to equalize opportunities for all people on the planet, we will need even more. There is no way around this. So, the prices, that's the other side of things. The more we produce, the cheaper it becomes. The prices are falling, and this is a challenge for people out there in the mines and for mining corporations. We need to produce more, but at a lower price ideally. And here, it's the 1950s again to the 1990s, and you see iron and manganese ore. Iron is particularly relevant here. You see the prices are fluctuating, but overall they are dropping. So iron is becoming cheaper. It's cheaper than it ever was, kind of, but we need more of it. So this is a challenge when you're out there in the mining operation. How can you do this? Produce more with less. So mineral resources, well, when we're looking at high-tech metals like the rare earths, well, the reality is that China holds about 95% of the high-tech metal market today, and it has, however, less than 90%, 95% of the world's occurrences. However, they're very good in terms of mining it. They have surface deposits that allow them to mine huge amounts of rare earth elements very efficiently and at very low cost, and there is no real competitor for this in the world. There is huge efforts now. The European Union has issued all sorts of directives now, already starting in 2005, but it has not actually resulted in any higher production. So while there's huge investments, at least in Europe and also in other parts of the world, like in the US, it hasn't actually materialized in any real result. So far it's tricky, and the Japanese have started to hoard rare earth elements. They have produced areas where they can store rare earth elements on the order of up to 6 months of their industry's supply. So this is in order to not be completely dependent on market partners like China here. China has a lot of control, and this worries a lot of people, including the European Union. This is why these efforts are being very strong right now. But so far, we haven't actually found the Golden Grail. We have no such deposits like they have in China, particularly in Mongolia, and we're not really competing all that well at this particular point. So, I'd like to now move on into different types of deposits, and I can only give you a flavor here. You will have to, if you're interested in this, you will have to go and do further courses or read up on this, but I'd like to give you really a first introduction here. So, in broad terms, one of the main categories of what many of these ore deposits are about is that they're made in a broadly igneous context, i.e. they're connected to volcanoes and magmatic processes. So one of the main things here is pegmatites, and we talked about pegmatites when we talked about granites. It's left over residual liquid and fluids very frequently with a lot of incompatible elements, and they can crystallize. This is where we make a lot of these very interesting mineral associations typical for pegmatite, and here we get a lot of minerals like mica and tourmalines, lithium mica for example. We get beryllium concentrations, and we also get gemstones there. We talked about the largest crystal on the planet being a beryl, and that it was found in Madagascar, being about 60 meters long, and that's also in a pegmatite. So pegmatites are very popular for that. And then we have layered ultrabasic intrusions. We talked about layered ultrabasic intrusions in the context of fractional crystallization in magma systems. And here we have, for example, some very famous ones like the Bushveld in South Africa, where chromite is mined. and then there's Sudbury in North America, and several smaller ones all over the world. So let's delve into pegmatites for a few minutes. This is a non-ore deposit rich pegmatite which I visited a few years ago on the island of Bornholm, which is now Danish. And here's a Danish coin for scale. It's got this little hole in the middle. And here is a giant K-feldspar. You can actually see the twin here. So this is how big the minerals grow there. And we don't fully understand how it works, but we must consider a lot of fluids involved. There must be super ideal conditions for these crystals to form, otherwise we wouldn't get these giant grown minerals. And if they are of any major relevance in terms of economy, then of course this is ideal mining ground. So here is an example from Evans' textbook. This is one of the main textbooks I recommend for beginners in this field. And here we have some country rock hanging in the footwall, and this is about 30 meters, so the diameter of this, or the width of this intrusion, this pegmatite intrusion, maybe about 50, 60, 70 meters. And here we see that it's not homogeneous, it's got sort of different phase sheets in it, and there may be feldspar concentrations here with F at the margins. Then there's beryl here, and that's the dotted area. And there's lepitolite, and that is the lithium mica, and there's quartz concentrations and spodumene, and they all are found in different areas. And depending on what you're after, you can then focus and try to get this out. Very frequently, you need to actually remove some other rocks in order to get to the rocks you want, and this often produces huge spoil heaps associated with mining. Unfortunately, that's not ideal, but that's often the way it has to be. So here we have a little diagram. This is from a textbook by a researcher called Mattis. And here we have high temperature magmatic stage, about 1000 degrees. Liquids and crystals are forming in association with each other. And this is the pegmatite environment at maybe 800 to 500 degrees or so. And at that point, we are increasing the vapor pressure, partly because crystals are forming like feldspars that don't contain a lot of water, and the volatile content in the magma increases until the vapor pressure is very high, and this is ideal conditions for making these pegmatites. And it's largely fluid controlled, we believe, and the fluid would carry a lot of these important elements that we are after. Maybe you heard about the little quarry at Itaby, and it's famous amongst geochemists and ore deposit researchers for the fact that it gave rise to naming several elements in the periodic table. There is yttrium, terbium, erbium, holmium. They all were first described in this little place. It's just outside Stockholm. It's now abandoned, it's not mined anymore. And here's one element, yttrium. There's yttriumvägen here, just very close to us. And it's by now a protected site, and most of these buildings are no longer there. But here's yttrium, terbium, erbium, terbium, etc. All of them were first isolated in this quarry, and it's a pegmatite. Here is Professor Johansson showing me around, and here you see the pegmatite rocks in the background. Originally it was mined for feldspar to make ceramics of it, so some of the fine kind of china that people were drinking their coffee from was made from material there. And they didn't quite realize that it was also a little radioactive. So I think by now people are not using this material anymore. And here you see some of the large feldspar things. Here you see a radial fracture pattern, probably because of fluids bursting or some sort of way. But here we have some darker minerals, but here we have the giant feldspars. Here's just a close-up shot. And intriguingly, the Americans have put this plaque up. It's to commemorate that this is a historical landmark, as it says here. 4 periodic elements, yttrium, terbium, erbium, and terbium, were isolated there. And some of the others come from close by in the area there. And this was put up there in 1889. It's rather in the forest now, so some people flock to there because it's a geologically important site. So having talked a little bit about pegmatites, I'd like to move on swiftly. Layered ultrabasic intrusions. This is a photo of the bushveld, and you see the chromite layers there, and that is rhythmically interlayered with other minerals. And here crystal settling may be one of the key processes, and particularly the chromite is very dense, it might settle efficiently. And there is various other examples, as I said, Sudbury, and huge efforts at the moment at the Skagerrak intrusion in Greenland to see whether this becomes economically viable. And what's of interest here is that there is these individual layers. This is again from Evans' textbook, and these are the chromite layers, and that's what's really quarried there, being a huge reserve for chromium, for example, and various other metals. How does this work? Well, we talked about replenishing these magma chambers and making rhythmic layers of minerals, and this is what people have suggested being the main reason for that, and they want to exploit magma mixing here. So here is olivine, chromite, silica in a triangle, and we're really at the outer edge here. And here we have the chromite stability field, here the olivine field, and if we start crystallizing some magma coming from here, cooling down, it might move towards this curve, and there it will crystallize olivine and chromite together, and eventually it will end up in the orthopyroxene field. If we have a magma up here and we are pumping a new magma into the system, so we can use the larger diagram now. If we have a magma here and we're pumping in a new magma in the system, then they might meet somewhere in the middle, and it can occur that you find, or the magma finds itself in the stability field for chromite, and then it will crystallize for a short interval, chromite only. And if this happens, then I think there's a good chance that we could make a chromite deposit at the base of our magma system, for instance. So here's the idea, here's some chromite for illustration, and we discussed that this is maybe an oversimplified view, but somehow we nevertheless managed to make these large concentrations. And here we may have olivine first, here's some chromite then, and then some other minerals may form, like feldspar, and they may make the next layer. And magma mixing has been widely considered, although there's very young research that also suggests that some of these chromite layers might be reaction products of different areas or different domains, different rock domains within these plutons. I am not entirely sure whether it applies to all cases. I think we might envisage that there is several ways of making them, but their occurrence in these layered ultrabasic intrusions is very pronounced. So there's a few more igneous type deposits that I'd like to highlight. There's kimberlite diatremes, and here we are after diamonds, for example. These are volcanic vents, and they, we believe, erupt material that's coming from the mantle. It's very ultra-basic material, and it carries these diamonds. Then we could have disseminated mineral deposits, and here porphyry coppers is the most pronounced one, and one of the key places is, for example, the Andes. There we have a lot of porphyry copper deposits. Hydrothermal ore deposits, where we have precipitation from hot aqueous solutions. They're often associated with volcanic environments as well. And then there's volcanogenic deposits, for example, SEDEX, sedimentary exhalative ones. We talked a little bit about black smoker environments in geochemistry. This would be kind of broadly speaking this type of deposit. So I'll show you some illustrations of this as well. Here we have some diatremes, kimberlite diatremes, and they may bring up these ultra-potassic magmas that we believe come very rapidly from the mantle, and diamond is only stable under very high pressure, 150 kilometers or so, so you must bring them up relatively fast, otherwise the diamonds would react to something else, carbon I guess, and then you lose them. So here we must envisage very rapid ascent, probably a very gas-rich magma. And we talked about diamonds the other day. De Beers is really, really keen on monopolizing the diamond trade. And here's the Oppenheimer diamond, just to give you a feel. Sometimes they come as yellow crystals, sometimes as pink ones, and they're actually particularly priced if they have nice color. And then there's, of course, the transparent ones. And this particular specimen is 4.5 centimeters long, one of the largest ones ever found. So if you find this guy, then you're made financially. But as you probably always know, there's always these legends that come with diamonds, that they bring bad luck for some reason. So maybe you will be financially well off, but maybe it's not good for you. I don't know. Anyway, another type of deposit here is the disseminated ones, as we said. And here we have porphyry coppers. They often are associated with late-stage volcanic features, and dissemination can occur as veins or as tiny little isolated, and they're often associated with a large alteration halo in the heart of a volcano. Here we have a standard kind of granodiorite type volcano down here with a granodiorite pluton feeding into a surface eruptive scenario, and there's all sorts of fluid migration and breccia vents, and this would be the area to look for these disseminated deposits. And copper and molybdenum and even silver is one of the main features there. The Spanish Empire for a long time was funded by extracting silver in the Andes, and they had some really rich deposits there that kept the empire going for a long, long time. So here's just a close-up. This is also from Evans' book. This is a stockwork type of molybdenite-bearing material, and here you have an indication of how the infiltration might have worked. I showed you this just a second ago, so you may find that you have tiny concentrations of copper, and as such, the rock itself is not very laden or very rich in copper, but if you mine huge amounts of it, that's where you can make up for the low concentration, and that's what is happening with these porphyry coppers. Very frequently we find that the ore is concentrated in certain ways. So if this is an intrusion, for example, it can occur as an inverted cup, or as a hollow cylinder, or even as a tabular one. And once you have found it, then you will usually explore a little bit of how exactly it's shaped. And it makes a huge difference, because if you want to quarry this, well, you need to really quarry a big hole, and the hole has to be very wide in order to get to all this. If this is your situation, much of your ore will be reasonably close to the surface, and you don't have to quite dig so deep, which is financially, of course, attractive. So, here there's various variations of this. It doesn't always have to be associated with a positive, i.e. a cone-shaped volcano. You may find that there is intrusive activity that is not manifested at the surface with a cone-type volcano, but you could have hot springs and features like that. And you might find that there's ore deposits happening in these scenarios as well. The exploration geologists, they will look particularly for alteration types in order to find these shells, and here there would be a low-grade core, and then in this case we have an ore shell, and there is a low pyrite shell. So in order to find these things, you would look for alteration and low concentration ore deposits, and then migrate towards higher and higher grades of ores. It's called vectoring, so that you vector yourself towards the ore, and this is a job for exploration geologists. So often it results in these giant holes in the ground, and they are not particularly attractive, I admit, but well, nowadays, once it's mined out, people are thinking about converting them to lakes and things like that, so they can be brought back as naturally active environments, should we wish that in the end. So, quickly, hydrothermal ore deposits that contains mineral that are precipitated from aqueous solutions, and they're often associated with igneous processes. And then we have these volcanogenic acidic deposits like black smoke environment. This is a photo from Indonesia, and here you see the huge amount of gas coming out of this particular volcano, and you can just about see the yellow stains here, so there's sulfurous gas, and gas is a very important feature for making these ore deposits. So here is one of the ore fields in southwest England, and this is a granite situation, and here we're looking at iron and tin in particular, but also copper and lead and zinc. And here we have again a pluton of some definition, and there is deposits of certain types of elements, metal elements of minerals in these areas. And here we seem to have association with fractures as well, so sometimes the local and the regional geology can play together, defining where exactly the concentration of your ores might be. So, as one more deposit that I briefly want to mention, here we have skarn-type deposits, and should your intrusions go by accident into a limestone-type country rock, you very often get reactions between the intrusion and the limestone. And you all know, if you put acid on a limestone, it'll fizz, it'll react very strongly, there's a lot of CO2 in there. And magmatic fluids would also be very aggressive, they can be very acidic, as we've discussed yesterday. And there you often get these skarn interactions. These would then be calc-silicate type minerals, and it leads quite frequently to deposition or precipitation of metals as well. We have a whole series of skarn type iron ores here in Bergslagen, and skarn is in fact a Swedish word. It's the rock that the miners didn't want. So it's apparently not a very flattering word, I understand, but it helps us to vector towards the iron ore again. Once you see skarns in a limestone type setting, you can probably anticipate that you're close to some sort of intrusion that potentially also produced some metals. So here we have a pluton. This particular one is from southern Africa, and you can see it's nicely circular. It's got some upturned rocks here in the vicinity. I don't think this is a particularly rich metal deposit, but here's some maps of various examples, and here you can actually see some circular or semicircular intrusive material that is reacting with a limestone, and in this reaction zone you get the skarn deposits, or here you have it the other way around. There's a tongue of limestone that was almost enclosed in some intrusion, and there you get these reactions. So they are intimately associated with intrusive material. Another form here could be that we have a felsic, in this case a felsic magma body, and we are feeding fluids to the surface, maybe in hot springs. You have seen images of geysers, for example, on Iceland, etc. And it's not uncommon that once these fluids interact with certain country rocks, in this case a limestone here, you might get deposition of various minerals because of the change in, for instance, pH. Limestones tend to be alkaline, as opposed to, for example, acidic fluids that come from volcanic situations, and once they equilibrate, you might find that the fluids lose the capacity to carry a lot of these metals, and they will then precipitate them. So these strata bound, meaning that they are associated with certain layers in the sedimentary record, these strata bound deposits, they may form because of chemical reactions, because of the bedrock again. So here the bedrock might be a very good guide for you in order to find ore deposits. Now, mid-ocean ridges are, as we discussed just yesterday, a prolific future resource potentially. Here we're making a lot of these sulfite deposits, and here's a nice image from a recent trip to China. And here's a black smoker. There's of course no smoke. This is all tiny little crystallites of minerals precipitating, and then they will form layers around, for example, the mid-ocean ridge. And sometimes we get them abducted into ophiolites. There we can mine them on the surface. But if we really want to tap into them as large resources, we will need to consider going, well, submarine. And this will likely take forms without a lot of humans being involved. I think we will have to think about mining robots and things like that for the future. But the surface of the ocean is a huge environment that we have not fully tapped yet. So, here just another impression of a black smoker. And this is how these things might look like. They form these lenses, as I said. Here's sulfites, here's the seafloor, and they often make these chimneys of material that will precipitate. These fluids are 350 degrees hot. They're very acidic as opposed to seawater, which tends to be a bit more alkaline, and the seawater is also cold. So these hot fluids suddenly find themselves in a chemically different environment, in a different thermal environment, and precipitation of crystallites is the consequence of that. I showed you this diagram in geochemistry, I think just yesterday or the day before, and here seawater is cold, it's alkaline, it's oxidizing, and it has virtually no metals, but the fluids that are exhaled here, they are up to 350 degrees hot, they're often acidic, they're reducing, they're sulfur rich, and they carry up to 100 ppm iron, 33 manganese, 7 ppm zinc, and 2 ppm copper. Remember the slide at the very beginning, 2 ppm copper is actually quite attractive. So here the idea is that seawater is percolating down and it's heated up, it's interacting with the rocks along the way, it's leaching several of these elements out of the bedrock, and therefore it's concentrating them in the fluid, and these fluids then rise up, and that's where we make the ore bodies in those areas. So, having talked about magmatic and igneous ways of making ore deposits, I'd like to spend a few minutes also on sedimentary deposits. So here we have banded iron formations. This is something that was happening in the early Earth, but we don't really make banded iron formations anymore these days. It's got to do with the oxygen in the atmosphere. And here we have placer deposits, and we have deep ocean precipitation like manganese nodules as well. Banded iron formations are one of the key sources of iron, and since we don't make them anymore, I will not go into them a lot. It's not a renewable resource, which is a tricky issue. So if we mine it all away, we will not have anything. But I'd like to talk a little bit about ethical mining, and here we can look into things that are renewed all the time, and placer deposits is one of them. Here we have concentrations of certain minerals due to stream action, and this is particularly important for gold. You probably all have heard about the placer deposit in Witwatersrand in South Africa. Huge reserves of gold there, and what happens is that a lot of the minerals are transported by water due to erosion, and they will concentrate in certain situations. And what we often need is some sort of a sediment trap. Here, this could be at the base of a waterfall where water has carved out some little depression. And here's just a picture of a Swedish little river, and all these little steps, each of them might actually constitute a place where you have concentration. And the bedrock could play a role here. If you have, for example, an upturned sequence of bedrock, and some units are more erosion resistant, you may actually find that you have concentrations of heavy minerals there. And if you have the right source area, well, this could be gold. Another way is meandering rivers, and we all know they're very dynamic systems, and we have erosion on one side, deposition on the other, and if you find the right loop in an old river system, then that's a useful place looking for gold. It's not just any old river, and it's not any random place in the river. There's specific areas in the river that you may want to target. Another way is that if you have rivers coming together, you might actually find that due to the current intermixing here, that you could create some shadows, flow shadows, for example, and this might lead to deposition of certain minerals. So if you find something like this in the geological record, this might be a good place to look for gold. So here, the density is incredibly important. Quartz has a density of 2.65, while gold has a density of 19. This is why it settles out. This is why you can wash it with a gold washing pan. And here's a gold nugget. And yeah, I guess this is what people still do these days up in Alaska. There is a lot of effort trying to get gold out of old placer deposits. And this we summarized, or this we said previously, could be bedrock geology, it could be sedimentary traps of some definition, it could be rivers joining, meandering rivers. But the best places you can find are actually not primary places, they're secondary places. This is when you have an old river system that's partly being eroded and recycled into another river. It's like double distillation. When you want to make whiskey, you know, people pride themselves if they double or triple distill whiskey because it gets apparently better and better. And I guess this is a similar thing here. If you distill the gold several times into new situations, you might get really high concentrations. And my understanding is that places like Witwatersrand, they are exactly things like that, multiply recycled gold that is then concentrated. How does it work? How do these nuggets form? Well, it starts off as a rock that has a little bit of gold, but gold is very soft. You might remember that you can actually bite gold. This is the ancient test for whether it's gold or not. And that means in a river that transports sediment, gold will actually be shaped. And you will break down the silicates with time. And here you have a gradation. Here we have a little gold. Here we have more gold. And this is effectively when all the silicates have been broken out and removed, then you get these golden nuggets. So it's a physical feature. The river actually shapes these gold nuggets. They don't occur like that in nature to start with. So we're moving further now, weathering deposits, and this is particularly important for aluminium. Our best source of aluminium is in fact bauxite, which is a weathering deposit, and bauxite is very important. We need a lot of aluminium for our air traffic industry, for example, for all the lightweight structures. More and more lightweight metals are used for cars because it will save us petrol and things like that. So here the idea is that we have a rock that has some aluminium, but instead of concentrating the aluminium by moving the aluminium, what happens here is that we're moving the other things away. We're weathering a rock and we're removing other components so that certain elements like aluminium are left behind. And then we have secondary enrichment processes. Here, for example, due to weathering, we might move certain elements into certain areas and then we precipitate them, and again we will find an enrichment. This is also known as supergene enrichment. There we have weathering, but we're moving the elements of concern into certain areas and concentrating them there, while in this particular case the elements of concern are staying where they are and we're moving the other things away. So for that we need a lot of weathering, and weathering is best done in tropical climate and with a lot of water. So fertile, water-rich areas are good for this. And much of the bauxite comes from Southeast Asia and also India, for example. And there is a bauxite smelter, an aluminium smelter in Iceland, for example. And there is no such thing as bauxite in Iceland. It's not the right climate zone for it to start with. And much of the deliveries actually come from Southeast Asia, but they're shipped there because the glacial water, the runoff water from the glaciers, produces very cheap energy. And it's actually cheaper to bring it to Iceland and smelt it there than smelt it in Southeast Asia because the energy in Iceland is so cheap. It's a bit of a bizarre situation, but that's what economy does. So here we have one of these situations. We have a basaltic volcanic rock, and it all comes down to igneous rocks usually, and then depending on the exact climate situation we might have weathering that takes away certain components but leaves behind others, and we might find that we get these laterite concentrations, and they can then be redeposited and you can concentrate them as is indicated here, but you need an igneous type of terrain and tropical weathering. That's the best combination to make bauxite. So bauxite looks brownish red, and here's some example. So it's the progressive dissolution of the other things like the silicates, and eventually we're left behind with these materials known as bauxite. The exact minerals you can look up, we don't have to go there today, but here's just some impressions of how this material looks like. So here we have alteration in the bedrock near to the surface, and this is not infrequent. So here we have altered rocks, for example, and this, in this case, a peridotite, an olivine-rich one, and we might have a residual laterite at the top from removing these things, and there you will find these nodular iron oxides, and there's a porous laterite, and here we have really heavily altered materials. So alteration becomes a factor again in exploration for this. You want to see really altered rocks. If you're a mining exploration geologist, then alteration is your friend. So you want to look out for alteration. If you're a geochemist and you study genuine high temperature processes, alteration is not your friend. So this is a different mindset. So one man's signal is often another man's treasure. One man's kind of, pain is often another man's treasure. And here you need to kind of shape your outlook, and then you may be very successful. So we mentioned supergene enriched areas, and this is, for example, a situation again involving weathering. And here we have a surface, there's the water table, and you might find that rainwater leaches certain components and brings them down. And the water table again might act as a chemical barrier, and you could actually get enrichment of certain metals or certain components there. So here I've just added a little bit of an arrow to signal that this material is washed down by water and you need some water to go with it. So this is the leached zone, and you might then have mineralization down here in an enriched zone. And these are the things we would then look for as mining or exploration geologists. So, a few words at the end. What is it we need to do as geologists in order to really help our society and industry? Well, what can we do to find more? Well, we need to think about the resource cycle. So, what people in our business do is usually being involved with this first step here, the mine or the source. It's about finding the ore and efficiently extracting it. But there's other things that play a huge role. It's about whether there's enough technology there in order to mine it efficiently. It's about investment. There needs to be equipment, for example. Then it's the infrastructure there. If you're in the middle of the jungle, for example, or in the high Andes, and you have no good way to extract the ore and bring it out, this could become very, very expensive. And these days, there is fashionable new concepts like making super quarries in areas that are not frequented very heavily by people, and often they may be even close to the sea so that things can be shipped right away rather than involving loads of lorries itself. But of course the market is important. But we have to be realistic. As geoscientists, as geologists, we really have our main aspect here. This is what we can influence. The other things are often out of our control. Intriguingly, the Geological Survey of Sweden has come up with this thing, which it did in, I think, the 80s. This is a logo I was sent by someone, which goes back to this initiative in the 80s. The Geological Survey advertised that if you sent in a rock that you find in your garden or somewhere, they would look at it and determine what it is. It was not about helping people to understand the rocks in their garden. It was about to see whether there's any valuable commodities in these rocks. So they effectively used the population as exploration geologists. I am not sure anything really came out of it, but it was an interesting kind of thing. And this was the logo for it. It means mineral hunting. So it was trying to instill the concept of exploration into the general population. But as I said, they don't do that anymore. So we must also recognize that certain types of deposits are linked to certain tectonic environments, and as geologists, this is a good starting point for us. So if we want to find certain types of ores, we may want to target certain tectonic environments. So here, for example, the deposit types, we will find massive sulfites, for example, at ocean ridges. So if you are after this is a good place to go. If we want to look, for example, for strata-bound situations, well, for copper, lead and zinc, then we would be looking at volcanic terrains in the widest sense, maybe here in a subduction environment. Or if we're looking for chromium, then we may want to look for igneous intrusions that have settled chromium out, and etc. and so forth. If you look for corona types, then you need to have some sort of probably continental subduction related system where you get this, and this helps a lot. One of my former PhD students, he works for a mining company, and his job is nothing else but trying to associate from the literature mining types or deposit types with tectonic environments and building up databases for this. So this will narrow down your search dramatically, and this is what we need to do in order to become more efficient, I think. So what can we do? Well, we can help with predictability of the geological context and this is what I just mentioned, so there we get better at actually finding them. We can identify these targets then more efficiently, once we know what to look for. Then, once we have found something, geologists can help assess stability, grade, workability of a deposit, and therefore help exploitation of it. And in the long term, there's a lot of jobs still today, also in Sweden, when it comes to monitoring mining safety and predict ore continuation in mines, for example. And I predict that some of you guys will actually do exactly that. If you work for LKAB or Boliden, then these are very important tasks up to the present day. So, mineral reserves for many common metals will be exhausted by our predictions within 50 to 100 years. So, a lot of people predict we are using a lot of metals. Each of us uses 700 kilograms of steel per year. Well, that's in form of cars and things like that, but nevertheless. So in Sweden, mining for traditional metals is going deeper and deeper. As I said, Kiruna is the deepest place in Sweden, and LKAB is priding themselves to have the deepest mine in Sweden. So, and it becomes more and more expensive the deeper you go. But Sweden has no tradition in green and high-tech metals, and China, as we said, is the market leader, and that's a huge challenge for Sweden as well as for Europe. So, this brings me to an end, and I'd like to say thank you for your attention, and I hope that that gives you a good starting point. And naturally, we can discuss this, but I think we're all due for a little break, first of all. Thank you very much.